Hi, I'm Cindy Blake, Senior Security Evangelist at GitLab. I speak with a lot of companies that are maturing their DevOps practices and trying to pull security into the mix, whether it's shifting left or securing their newest infrastructure as they modernize their applications. I hope my experience can provide some practical advice as you think about securing your infrastructure as code while moving towards security as code. And I'm happy to take questions in chat throughout the presentation. Now, the two terms are very related. What is security as code? To get there, we really must start with infrastructure as code. So let's look at the rise of infrastructure as code. In the beginning, developers created code on hardware provisioned for shared use. The developers had to ask operations to provision hardware for them before they could get started, and every project was unique. With cloud, developers still ask for hardware to be provisioned, whether it's from their IT ops or their cloud provider, and it's still on someone else's hardware, but it can get done really quickly and efficiently, so developers can get coding more quickly. But still, every project is unique. And all it takes is a little configuration. Now, to speed configurations, people started using templates. Then someone said, hey, I can code those templates to automatically provision the resources needed. And that gave rise to infrastructure as code. So cue the Star Wars music. With everything, including infrastructure, becoming code, developers can provision hardware themselves. And now it's even faster and more consistent. And again, all it takes is a little configuration. With configuration settings everywhere you turn, in cloud services and containers and orchestrators, in your software build and deployment tools, it's no wonder we're worried about misconfiguration. With automation, policies can be configured centrally and applied consistently to all projects. We've removed some of the individual decision-making and its potential for error, but we've created a centralized target for anyone wanting to inject malicious configurations. And therein lies the danger. Configuration can be automated, repeatable, and follow standards. Or it can be a mess with a nasty web of one-offs created without understanding the impact of the choices. Either way, security must be considered for not only the hardware and the apps, but the infrastructure upon which the apps depend as they're developed, deployed, and used. And this is why security pros cringe. I love this report by Snyk on securing infrastructure as code. The first point's not surprising. When you look at threat reports, whether from Verizon or Fortify used to do them, AT&T, whomever, the vast majority of attacks are not inventing new approaches. They're using tried and true attack paths that have worked well and continue to work well. And historically, attacks have leveraged vulnerabilities in the code, but they're beginning to leverage vulnerable configurations in the apps surrounding infrastructure. The second point is that few are confident that they can spot bad configurations. That really should be no surprise. Do you even know where all the configurations are, the options that are available, and who has access to change them? So it's really a no-brainer that automation can help. Capital One was merely one example of an exploit of a misconfiguration. Automation must go way beyond the use of cloud and configuring the cloud settings alone. It's really a huge risk and gets worse as more applications are re-architected to be cloud native. In fact, I'd like to share this famous quote. Misconfigurations will be on par with failure to patch in terms of top exploits. When? Well, now and into the future. Wikipedia defines infrastructure as code as the process of managing and provisioning computer data centers through machine-readable definition files rather than physical hardware configuration or interactive configuration tools. It enables scale, speed, consistency, visibility, traceability of changes made to each configuration. But like source code or dependencies, it really deserves version control, access control, security scanning, and monitoring, just like you would do for any other code. The challenge is there's so many levers to pull. Do you even know where they all are? Do you know the optimal settings to use? If these code settings are codified in infrastructure as code, do you treat that code with the same rigor that you would application code? Security as code codifies security and policy decisions, automating them within workflows across functional teams. Now, it's easier said than done. You must define the processes and automate them, and define the policies and automate those. A lot of people get stuck on the first step, shifting left, or they try to apply policies without enough thought into the processes themselves. So I've summarized a few of my recommendations for security as code into 6 items. We'll go through each of these in more detail, and you'll need to think about the processes and the policies for each. First, test your source code. Most people use SAST and dependency scanning, but also think about secrets and even coverage guided fuzz testing. Next, think about your code's execution. You need to go beyond pen testing with automated dynamic scanning and maybe even behavioral fuzzing and API testing. You need to test the application's infrastructure. Think there about containers, packages, and configurations. And then test the infrastructure as code, testing, managing, monitoring, and protecting code configurations, things like Helm charts, Terraform, and the like. And then you need to think about testing protecting the access to the application and its data. And that goes beyond traditional network security. You need to think about containers and orchestrators, which I tend to think of as micro networks. So think network security just at a different level. And finally, think about securing the software factory itself. Access to the code signing, push rules, and all of those things along your entire software development lifecycle. Now, yes, the lines are a little bit blurry between items 3, 4, and 5, but that's so in real life too. So let's break down the effort a little bit more. You must define the processes and the policies around each. So for instance, you test your source code. Do you test every app? What are the exceptions? Who can approve the exceptions? Do you test your containers? When? By whom? Do you monitor east-west traffic among the apps within a cluster? What's allowed? What's not allowed? Who has access to your application code, to your infrastructure as code? What are they allowed to change? All of these things need to be thought through. So let's start with items 1 and 2, testing the code. Most people start with shift left. It's really a fundamental step towards automating security. You should be testing the static code and also its execution. Let's look at a few things you might not have thought through. As I talk with customers, these are the main reasons they want to shift left and automate security testing within their CI pipelines. And consistency is one of the top reasons. Usually it's even above reduced security exposure. They kind of go hand in hand. So automation can not only simplify AppSec testing, but make it easier to ensure that the scans are actually used and that the appropriate consistent action is taken. This automation can greatly simplify an audit as well. Ideally, you'd want to run multiple types of scans, both at code commit, before the code is merged, and as it's merged into the main branch. Most people start with SAST and dependencies and add from there. Consider tools that have all of these scanners built in so you don't have to go crazy managing this a complex tool chain integration. Even DAST can be run at the point of code commit before a merge if you're using a DevOps tool that provides a review app to assess the impact of code changes. That review app, which is ephemeral in nature during the build, reflects the changes made to the code, and it too can be dynamically scanned at the point of code commit. So first think about what scans will you execute. Determine what scanners you'll use and the scope on which you'll use them for your application portfolio. Next, determine policies around what you'll do with the results of those scans. When vulnerabilities are found, what actions do you want taken? Ideally in an automated fashion, but it's important to think through that even if they're addressed manually. I would encourage you to think about fuzz testing. Fuzz testing was once in the realm of only really the super geeks, and that's not so anymore. When fuzz testing is integrated into the developer's workflow, it's easier to set up and interpret the results, making adoption much easier, essentially mainstreaming its use potentially. Fuzzing blurs the lines between what is a security flaw versus a quality or logic flaw. Behavioral fuzzing can be very helpful to test your APIs, which are an important element of modern application infrastructures. Now let's look at items 3 and 4. Testing the app's infrastructure and the infrastructure's code. They're not exactly the same thing, so let me explain. I mentioned APIs. As monolithic apps get broken into microservices, authentication and authorization takes on a whole new dimension and embraces more use of APIs. Are you testing them? Can you go beyond testing and to capture, store, and view all of the API calls for audit and compliance purposes? Additional attack surfaces to consider include containers, more specifically, what's in them, the libraries and the dependencies, along with orchestrators. Orchestrators are configured to direct how and where and what and when containers run, including that API architecture. But think about which apps can talk to which other apps, what compute and storage resources each app is allowed to consume. And then there's the cloud environment itself. An environment hosting virtual machines and containers, it represents an attack surface as well, though it's really more closely guarded than these other newer elements. Each of these items has configuration levers, each an opportunity to do it wrong, either uniquely by projects or repeatedly across all projects. That's the difference between infrastructure, which is unique, and infrastructure as code, which is used repeatedly and consistently. You must define your execution policies for those infrastructure elements, along with any templates or automation you use to configure those elements. What policies will you use in dev and prod for things like containers, packages, Helm charts, and the like? And what will you allow or deny for each of those policies? What triggers an alert? What's acceptable for remediation? You can think of it sort of as a service level agreement. What exceptions will you allow and who can grant them? Step 5 is to monitor and protect the network, not just the traditional network access, but the micro network within and among containers. There are a couple of technologies that can be readily applied. So the first is container network security. You can think of it sort of as a mini firewall inspecting traffic inside your Kubernetes cluster. You can set up what traffic between pods is allowed or denied, and that can prevent attackers from traversing laterally from one application pod to another within a cluster. Next, consider container host security. Think of that as intrusion detection and prevention for pods within your Kubernetes cluster. It can configure what resources an app has approval to access, for instance. Just yesterday, I was talking with an industry analyst about this, and he said he's seen some large enterprises setting up hundreds of clusters. I'm guessing that they feel that segmentation is safer, but it's also probably a lot more overhead to manage. And customers we've encountered have far fewer clusters, instead managing multiple namespaces within a cluster. And I just wonder if cluster sprawl can be avoided by using better security within the cluster, something like container host security and container network security. So something to ponder. For step 5, securing your application's network, again, lay out which policies must be applied to which elements. Are you going to use WAF? Under what circumstances? Will you use container security everywhere or only for certain projects? Next, again, think about what is allowed and what is not. What's an alert but will be allowed to continue versus what pushes the stop button for your software factory? And saving the best for last, speaking of the software factory, this is a huge issue now, thanks to the attack on SolarWinds. It made everyone ask themselves, am I doing enough to protect my software factory from the same threats? The short answer is probably not. Even the most damaging attacks tend to rely on complacency toward basic security hygiene. Think patches and passwords, using tried and true exploits that have been around for a long time. From what I've read in the news, SolarWinds admin relied on a simple password and didn't change it. My advice is to revisit your software security policies. Apply automation whenever possible to make it more likely that policies are applied consistently, things like regular key rotations. Use secrets detection to look for hard-coded passwords that are especially prevalent when you're using APIs. Think really carefully about alerts versus alert fatigue. You really want to minimize the alerts to those things that are truly important, and think about audit processes and exceptions. If you can minimize things, potential exceptions through automation, it can narrow what you must look at uniquely in an audit. For the SolarWinds Orion app, code was injected during the build process. The attackers also included safeguards to prevent backdoor lines of code from appearing in Orion build logs. And they also included checks to ensure that such tampering wouldn't cause build errors. Your log should show who introduced a code change, whether the build failed or not. In this case, even digitally signed code wouldn't have helped, though, because the Trojanized component was digitally signed and contains a backdoor communication with third-party servers controlled by the attackers. So what can you do? Think again about defense in depth. The attackers use multiple methods, and you'll need to use multiple defenses. I've tried to condense these suggestions into a short list. What's not here is start with good hygiene, scan everything, and look carefully at your access management, your password policies, and secrets management. But here's a few other things you might not have thought of. Automate your CI/CD to apply common controls. Every compliance regulation or regulatory requirement relies on common controls. These are things like if the person that changes the code shouldn't be the one that pushes it to production. There's several others. And if you're going to get the link to these slides where I've included links to more detailed examples that we don't really have time to go into here, but be sure and look at common controls. Next, apply zero trust principles. That includes things like least privilege access, not just to the network, but to your DevOps tool chain. GitLab's security team has several blog articles on best practices that may be helpful. Also, check more obscure things like container registries. Who has write access? A compromise of one person could potentially lead to a compromise of the container registry, which could lead through pipelines to compromises of numerous projects. Conduct an asset and access inventory, and be sure and include infrastructure elements that you may not think about, things like registries, package managers, and so on. Who has admin access, for instance, to these and to things like Kubernetes? Number 4, apply container scanning and SaaS to scan your Helm charts. Consider using container host security and container network security that I've just reviewed. And open source tools like Falco and AppArmor, that's a tongue twister, when used in a CI environment, can alert and prevent build servers from doing unexpected things like modifying scheduled tasks. Automated builds may also help here. The Teardrop malware loads directly in memory, and so it doesn't leave traces on the disk. The ephemeral nature of that automated CI environment could possibly wipe the malware on a build, but I wouldn't rely on that alone, but it could potentially help. And last, traditional AppSec testing looks for known security flaws. You may want to add fuzz testing because it's useful to find things that are not purely a security flaw, things that don't have a signature of a known CVE. But misconfigurations can be kind of borderline, as well as other potential flaws there that don't have a known CVE. And that's where fuzz testing can potentially play a role. Long term, you need to think about compliance management. Compliance frameworks are pretty basic around securing the SDLC or software factory itself. You'll want to consider more controls and enforcement beyond those basic. Things like approvals to merge code changes. Do I scan all my code? Not just the mission critical. Can I scale my current AppSec methods to the extent now required? These are important long-term considerations to think through. If a nation state attacker puts you in their crosshairs, it's quite likely they're going to find a way in, no matter how much defense and depth you use. You know, as the saying goes, they only need to be right once, but you need to be right every time. But if a breach does occur, auditability can make the difference for rapid detection and remediation. In your software factory, can you tell who changed what, where, when? Can you see all of the code changes for the code and the environments upon which it relies? It's really hard to do if you're using a bunch of tools bolted together in a complex tool chain. You lose that transparency as you traverse tool to tool. Take a fresh look at how you integrate security into your software supply chain and across your DevOps effort. When you approach security as code within your DevOps or your DevSecOps, as the case may be, you can have end-to-end security from software development through delivery and production, protecting not only the app, but the infrastructure upon which it relies. So how can you apply what you've learned today? Next week, start with identifying the access to the application infrastructure and think out of the box. Think about the infrastructure elements as well. In the first 3 months after this, determine your 6 processes and the policies surrounding each. This is really where the bulk of the work happens. If you haven't integrated your security scans into your CI pipeline, that's a critical first step towards automation that will help your security efforts keep up with those modern apps and their infrastructure. But you also need to think beyond shifting left. Think about all of the processes that need to be automated and the policy enforcement around each of those. So what am I going to automate? What's the scope of that automation? And what policies are going to be applied under what circumstances? So what are they going to allow and deny in that software factory and in my overall processes? So with that, I'd like to move to questions and happy to take questions live.